Hi, this is non-ideal solution. In the previous video, we talked about ideal solution. Ideal solution, how it obeys Raoult's law. How such a solution can be separated as pure liquids, the more volatile as distillate and the less volatile as the residue in the fractional distillation. In non-ideal solution, such a thing will not happen. You cannot separate the components in the pure stage. If one of the components can be separated in the pure state, then the other cannot. Other will be separated as a mixture, as a constant boiling mixture, what we call an azeotrope. Don't worry, we shall be discussing the details. If one of the components can be separated in pure state, the other component will remain as a mixture throughout. That is called an azeotrope or a constant boiling mixture. That is the property of a non-ideal mixture. Though the two liquids are mixable in all proportions, but they form a non-ideal mixture because their speciality is they at some composition they form a very, very exotic concept, solution. A mixture is called the azeotropic mixture. That beauty of azeotrope will come only in non-ideal mixture. Let's see what is non-ideal and how they are different from ideal. Now, there can be deviation from Raoult's law. You know, the Raoult's law graphs were straight lines, but there can be deviations. I'd like to use one blank page to tell you what is deviation. Supposing this was our graph. That was our vapor pressure graph. My lines are always not straight. They are curved. Approximately straight line. Supposing this is our A, this is B. Supposing B is more volatile. This is less volatile. In the earlier video, we took B and the left y-axis. But B was more volatile, but we have kept it in the right side. And this is the composition mole fraction. So, supposing this is A 100%, that is mole fraction 1. So this is A gradually decreasing. And say this is more volatile means here. So B gradually decreasing. And this is the total graph, right? This is for the ideal solution. The variation is linear. Both the individual partial pressure, this is PA, as A percentage is decreasing, the partial pressure is decreasing. This is B graph, PB graph, and this is the total graph, right? This is an ideal situation. But in reality, when we plot the graph on experimental observation, we do not find a complete linearity. There is a deviation, right, like this. You know, the vapor pressure graph for B might be like this, slightly above or slightly below. If it is slightly above, this is called positive deviation. If this comes slightly below, this is negative deviation. Similarly, the vapor pressure for A graph can be slightly above or slightly below. If above, this is called positive deviation. If below, it is called. Similarly, for the total pressure, it can be slightly above or slightly below. So these are small deviations which are inevitable. Even if small deviations happen, but still the mixture behaves more or less ideally. Why? Because you can separate the two components almost in the pure state in fractional distillation. As long as the two components can be separated almost pure in pure state, you can brand it as ideal. But if the deviation, now you see, in case of the total graph, the vapor pressure, the total vapor pressure is above the expected line. This is the ideal line, and the actual line is above it or below it. If it is above it, none of the points, it is like this, none of the points is going above this mark. This is the vapor pressure of pure B, more volatile liquid. So although the total pressure is not in accordance with the linearity, it is a slightly curved situation, but in no point it is going above, no point it is going above the vapor pressure of the pure B, more volatile component. Similarly, if it is a negative deviation, the vapor pressure is no point is going below the vapor pressure of pure A, the less volatile component. It is curved, but not deviating in a large scale, so that at any point, can you believe, in between the two pure state, the mixture has a boiling point or has a vapor pressure which is in between. If the vapor pressure will be greater than the greater among the two, then that is a highly deviation system. That is a large deviation situation. We call such deviations produce non-ideal solution. Mild deviation are inevitable. Many ideal liquid mixture, they show little deviation. Still we accept it as ideal mixture. They do not produce any harm while we separate them in fractional distillation technique. But if for a range of compositions like up to this, the vapor pressure of the total vapor pressure of the mixture is above or is greater than the vapor pressure of the more volatile component, then that creates a problem to behave in a different manner, as we shall see just after a bit. Hold on. Small deviation, you forget. Small positive and negative deviation take place when vapor pressure composition graphs show curves lying either above the linear graphs or below the straight line graphs respectively. If above, it is positive deviation. If below, it is negative deviation in the vapor pressure graph. But in no place the vapor pressure exceeds the vapor pressure of more volatile liquid, that is for positive deviation, and in no case, no range of composition, the total pressure goes below the vapor pressure of less volatile liquid, that is for negative deviation. Such liquid mixtures still behave as ideal mixture, as they can be separated completely in a pure state by fractional distillation. Now, when the deviations are large, when curves are largely deviated from the straight lines, then the mixture form non-ideal solutions. Non-ideal mixtures do not obey Raoult's law, and such mixtures cannot be separated completely in the pure state, at least for one component. Let us say at least for one component. One component can be separated in the pure state, but the other cannot. The other will be always a mixture, and that is called an azeotrope. I am just sounding you the term azeotrope, as we shall be very excitingly discuss about that concept, azeotrope concept, just after a bit. Hold on. As I have already told you, there are two types of deviations, positive and negative. Let us focus on non-ideal solution with large positive deviation. Small deviations are no doubt deviations, but they are just ignored and the solution behaves as an ideal solution. But what is the concept of positive deviation? Maybe small, maybe large. If the intermolecular forces existing in A and existing in B are greater than when they mix, the intermolecular forces become poorer, weaker. In that case, what happens? The vapor pressure becomes greater. The individual partial vapor pressure as well as the total pressure are more than those calculated by Raoult's law, right? The pure liquids have stronger intermolecular forces than when they are mixed. When they are mixed, they become poor in their association. Therefore, the partial vapor pressures and the total vapor pressures over the liquid mixture are much greater than their ideal values calculated from Raoult's law. Therefore, the graphs, they appear above the lines, straight lines, the respective straight lines, and they show a distinct maximum point, a range. The total pressure at some range of composition is even greater than the vapor pressure of pure volatile liquid we have taken as B. So don't always memorize that always B is more volatile. Thus the curve gives a maximum point which has the highest total vapor pressure at a particular composition. I repeat, at a particular composition, and that composition is called an azeotrope. This composition. I told you this composition. I have drawn that this composition is called an azeotrope. Supposing this composition is C may be closer to B, let's say 80% B or 0.8 mole fraction B and 0.2 mole fraction A. Supposing is the azeotropic composition C. C is called the azeotropic composition or azeotrope. And it varies from mixture to mixture, from non-ideal mixture to non-ideal mixture, showing positive deviation. Right? So, why such a thing happens, I'll tell you just after a bit. Now, what is the consequence? The consequence of positive deviation is del H mix. The enthalpy of mixing is positive because more heat is to be absorbed for breaking down stronger forces. Less heat will be evolved with weaker intermolecular forces between A and B. Therefore, the net result is absorption. So it is an endothermic mixing with a cooling effect. You can experience that if you mix those two liquids. For example, ethanol and water is a classic example of positive deviation. So I used to say to my students that ethanol and water, chemistry has branded as non-ideal mixture. But I'm sure when you grow little older and try to earn money, in that case, most of you will definitely have a taste of ethanol, alcohol in different forms, maybe rum, whiskey, wine, beer, and many others. You will definitely experience that. But undoubtedly, make sure that it is a non-ideal mixture. That has been proven by, I'm just correlating the scientific facts with the occult thing. Please don't take it seriously. So undoubtedly, alcohol is not meant for our biological system, but even then, the nature will demand to experience the effect of alcohol in the body. So this is in a lighter vein, just forget it. Now del H means 6 positive, there is an endothermic. What I was saying is you add a little alcohol, pure ethanol, that is absolute alcohol with water. Shake it immediately and you hold it in your hand in a test tube. You will experience a cooling effect because it will absorb a net quantity of energy from the surrounding, and there is a change in volume. The volume of mixing is positive, means the net volume increases due to decrease in the net intermolecular forces. The molecules are segregated, separated, the intermolecular gap increases, so there is an expansion. 50 ml of ethanol mixed with 50 ml of water will have a volume greater than 100. So here mathematics fails. 50 plus 50 is not 100. It is 100.2 or 100.1. That depends. I cannot say you what will be the volume. That depends between the two liquids. I have no idea at what will happen. But I have the idea that the total volume will be more than the sum of the individual volumes because of decrease in the intermolecular forces. Examples I have already told you in my first slide that they belong to different classes, not belong to the same homologous series. They belong to different classes of intermolecular forces. Like ethanol and water, I told you even if they belong to hydrogen bonding category, but ethyl group is non-polar. So presence of ethyl group reduces the degree of hydrogen bonding 50%. And as a result of this ethyl group, the mixing is not ideal. Though in 100% mixability, but it is not ideal, which means that at certain composition, the vapor pressure becomes much greater than expected of ideal behavior. At that point of the graph, the peak portion, intermolecular forces become very, very less. Very, very less. So more vapor comes out, and at a particular composition, maximum vapor comes out. The intermolecular forces become weakest at the azeotropic composition. Like cyclohexane ethanol, benzene acetone, acetone carbon disulfide. This is dipole-dipole attraction type, this is non-polar. Ethanol is hydrogen bonding, this is dipole-dipole attraction. Acetone dipole-dipole, this is simply London dispersion forces. Cyclohexane ethanol. These two, I told you a hint that when you find two liquids of different classes, organic classes, but mixable, then definitely they are positive deviation. Non-ideal with positive deviation. But how can you know which mixture is a negative deviation? Hold on. Don't worry. Now I shall show you the graph. This graph is mild deviation, which I had already drawn that it is above positive deviation, but very small curve. Curvature is very small. So at no point it is exceeding this line. My straight line is always funny. So in no point this graph is exceeding the vapor pressure of pure B. B is more volatile. I am copy pasting pictures from different sources. In some place B is more volatile, A is less volatile. But I have tried my best to keep more volatile as B and less volatile as A. I have selected such pictures and I have just interchanged the axis, the sides. In some case I have taken in the earlier video, I have taken B, the more volatile liquid in the left y-axis, and now I am taking in the right y-axis. Doesn't matter. You have to connect from the origin of this point to the opposite origin, that point to the opposite origin, and connect these two maximum points, and the pure liquid points to get the total pressure graph. Now these deviations, both partial pressure of individual liquids, vapors, and the total pressures, they do not create much problem. This is small deviation. Although it is deviation, positive deviation, above the ideal line means positive. But still we approximately take it as an ideal mixture because they can be separated in the pure state. But see, if the deviation is large, so that for a range of compositions, the vapor pressure goes above this line, the vapor pressure of the pure more volatile component B, in that case, situation becomes very, very interesting. So in these portions, the intermolecular forces between A and B becomes minimum, much less. Because that particular range of composition makes the intermolecular forces to loosen, to decrease to a large extent. As a result, the vapor pressure is more. So much so that at the maximum point, some miraculous thing happens. I'll tell you just now. B is more volatile than A as usual, but in this graph, XB is 1 is taken in the right y-axis. And in the previous graph, the more volatile B was taken in the left y-axis, which I have already told you. Now, let's take up non-ideal solution with large negative deviation. That means the graph, the real graph, the actual graph will come below the ideal graph in a very, very large deviation. Small deviations we can ignore. But large deviation going below the vapor pressure of the less volatile liquid A, that becomes very, very interesting. So in that case, the intermolecular forces of the individual liquids is less than when they mix. Their attraction becomes more. The intermolecular forces are stronger in the mixture than in the individual liquids. This is due to inter-ionic attractions. Most of them, they form ions by the reaction, or stronger hydrogen bonding interactions that makes the mixture more compact, more strongly associated. So there is a decrease in volume. Heat is evolved because more energy is evolved by more stronger intermolecular forces than expended by during breaking of those weaker intermolecular forces. So there is, therefore, the partial vapor pressures as well as the total pressure over the liquid mixture are lower, are much lower than their ideal values calculated from Raoult's law. You can have the total pressure, and at total pressure at some range of compositions is even lower than the vapor pressure of less volatile liquid. Thus, the curve gives a minimum point. In the previous case, it was giving a maximum point because it was positive deviation. Here it is negative deviation, gives a minimum point which has the lowest total vapor pressure at a particular composition. That is also called an azeotrope or azeotropic composition. Now I show you the graph. Now before I show you the phase diagram, phase graph, I am saying you that heat of mixing is negative. It is exothermic mixing with heating effect. You just do an experiment. Don't do that. You add two liquids, say nitric acid and water. Don't add concentrated sulfuric acid or pure sulfuric acid with water. You will land up with explosion, catastrophic situation, so be careful. So if you do so and hold your hand on the tube, you will find a huge heating effect because it is highly exothermic. So such mixture will have a net release of heat. So del H mix is negative and there is a decrease in volume. The volume change is negative. The net volume decreases due to increase in the intermolecular forces. They come closer, the intermolecular gap is reduced. So 50 ml of water mixed with 50 ml of sulfuric acid has a total volume which will be less than 100. Mathematics also fails here. 50 plus 50, in that case it may be 101, 100.5, 100.1, but it is 99.5, 99.7, but not 100, less than 100. And now the trick is all acid, inorganic acid with water, they are negative deviation. They are all non-ideal with negative deviation. Nitric acid with water. And acetic acid with pyridine. Acetic acid is an acid, pyridine is an organic base, acid base. Phenol is an acidic, aniline is basic. Chloroform, acetone. So you remember a mixture involving chloroform and another a polar molecule, polar solvent will be of this type. Chloroform, benzene belongs to this type. I will tell you why. Because some of them produce ion. Nitric acid reacts with water to form hydronium ion and nitrate ion because of the attraction, inter-ionic attraction. Earlier there was hydrogen bonding interaction. Now it will be augmented. It will be reinforced by ion-ion interaction. Inter-ionic attraction makes the cohesive force stronger. They come closer, more energy will be released, so it is highly exothermic. And chloroform acetone, I will just tell you what happens when you add, this is acetone and this is chloroform. Presence of 3 chlorine atoms is so electron withdrawing that this hydrogen has a plus delta charge. Although carbon hydrogen bond is in most situations is almost non-polar, but in this molecule is highly polar, is a strong plus delta, partial positive charge is here. And so also here there is a partial negative charge and there is a strong interaction. We can brand it as a hydrogen bonding interaction. Because of the strong hydrogen bonding interaction, when the two mix, chloroform acetone, that produces negative deviation. The vapor pressure is reduced as less vapor escapes from the surface because of greater intermolecular attraction. Most of the examples belong to the acid-base type, which produce ions, thereby increases the interaction by inter-ionic attraction. Right? Now let us see the graph. Unfortunately, here once again B, which is more volatile, I have put it in the left y-axis. That I did in my first video on a binary mixture. That is Raoult's law. And here, this is the less volatile liquid A is equal to mole fraction 1. This is B mole fraction 1. And all the graphs are lying below individual partial pressure, is deviating large. So individual partial pressure, this is liquid P2, this is liquid 2, or I have called it B, and this is liquid 1, that is I have called it A. So this is the partial pressure of B varying or 2 varying, deviating to a large extent from their ideal value, and this is A varying, deviating large, and this is the total pressure ideal graph, and this is the actual graph. And for this range of compositions, you find this is lower than the vapor pressure of the less volatile component. Right? So at this particular composition, the intermolecular forces becomes much greater, so much so that the vapor pressure is going even below. It should not go below. If it is an ideal solution, the intermolecular forces will be in between and the boiling point is a weighted average. But you see, after some time, I will tell you the boiling point graph. You will be simply astonished. At this particular point, what miracle happens, we will be knowing after a bit. When the intermolecular forces are much stronger than, the intermolecular forces in the less volatile liquid. For example, this is sulfuric acid, is the less volatile liquid, having a boiling point of 270 degrees centigrade, while water is 100 degrees centigrade. But in this composition, you will find the intermolecular forces are so strong that the vapor pressure is much below than the vapor pressure of pure sulfuric acid. As a result, the boiling point will be much higher. More is the vapor pressure, less is the boiling point. That will be found in positive deviation. But here less is the vapor pressure, more is the boiling point, as we shall discuss the boiling point graphs for both positive and negative after a bit. You understood? So this point, the minimum point here is called C, that is the azeotrope composition. There something miraculous event happens. I'll tell you that. Let us talk about the boiling point composition graph. Let us talk about the boiling point composition graph for positive deviation, then negative deviation. Since the total vapor pressure at all compositions are greater than their ideal values, the boiling points of the mixture are lower than their ideal boiling points. I told you a slight curve for the boiling point graph of an ideal mixture, not a straight line, slightly curving downwards. But this will be a larger deviation. So for positive deviation, where the vapor pressure is greater than their ideal values, the boiling points will be lower than their ideal values. But for a range of compositions where vapor pressure were greater than the more volatile liquid, the boiling points will be lesser than the less boiling component, that is more volatile component. Just the opposite. The minimum boiling point occurs at the azeotropic composition, that where the vapor pressure was maximum. There the boiling point will be minimum. Such a mixture at that particular composition is called an azeotrope, or a constant boiling mixture, or in this case it is called a positive azeotrope, or a maximum pressure azeotrope. Pressure maximum azeotrope, I'll tell you in my next slide. For example, ethanol water, which is a non-ideal solution of positive type, positive deviation. Therefore, I used to tell my students that ethanol water mixture is a positive deviation to your moral values, moral thinking. Of course, those who belong to the cold countries, if at all, you are watching, maybe after 10 years, 15 years of my death, even then, ethanol water mixture is not ideal. But because you are in a cold country, it is sometimes medically prescribed to take medical doses, prescribed doses, not super doses to be drunken with that. That's what I'm saying. So ethanol water has an azeotropic composition 95.6% W by W. In the earlier cases, when we were talking about vapor pressure, we were taking mole fraction. But here I am making a deviation, because in all literature you find the composition of the azeotrope as W by W. Therefore, I thought worthwhile to present the phase diagram of boiling point versus composition in terms of composition, in terms of W by W %, not mole fraction. That also happened in our ideal mixture, where you had encountered a smooth convex lens, a slanting convex lens from the slanting downwards from high boiling liquid to the low boiling liquid, from the low vapor pressure liquid to the high vapor pressure liquid. So that was there. But here you will find two convex lenses joining at a particular point. That's the beauty. So there also, in a single convex lens type of situation, in ideal mixture, the x-axis was W by W %, mass %. I have not shown because there was no point in discussing that, because that is an ideal situation. The successive distillates will be heading towards B, or more volatile component, and the successive residues will be heading towards less volatile component. So there was no point, there was no need to say about it. But now I emphatically say that the x-axis will not be in mole fraction, it will be in W by W %. Now, at the percentage of 95.6% ethanol, that means about 4.4% water. At that composition, if you get such a mixture, it will be corresponding to the azeotropic composition, corresponding to the maximum vapor pressure, total vapor pressure at this composition. Here, at this particular composition, the intermolecular forces is the minimum, for which the pressure is maximum and the boiling point is minimum. Now see, the more volatile component, which is ethanol, has a boiling point of 78.2. But the more volatile component ethanol has a boiling point of 78.5. But I would feel like correcting it to 78.4, because I have seen in many literature it is 78.4. But one author wrote 78.5. So I will go with the majority of the authors who give the data 78.4 degree Celsius, that is for pure ethanol. But azeotrope having 95.6% ethanol and 4.4% water has the boiling point which is lesser than this 78.2. You may be wondering, the small decrease is of no use. 78.4 and this is 78.2. Yes, for this it is small decrease, and for others it may be large decrease. But this small decrease makes it a special solution. How we shall know what is this speciality? This 0.2 difference is not much so far as the magnitude is concerned, but so far as the property is concerned, it is of remarkable importance. Have a look. This is, I was telling you, there are two convex lenses. If it is a positive deviation, then the convex lenses are stooping downwards. If it is with negative deviation, the convex lenses are stooping upwards. Because you know the boiling point, this is the boiling point graph. You forget about this. This is the vapor composition. I showed you even in ideal solution graph. I have shown you that this convex lens, it was extending up to this, to the end. But in non-ideal, it will break up. It will break up into two, one small, one big, or two equally big or equally small, equally big or same dimension, but meeting at a particular point. I'll tell you that later. But this is the liquid boiling point graph. This is the boiling point graph having a minimum, because the vapor pressure was going above the line, the boiling point will go, but the composition C remains the same. Wherever you found the maximum vapor pressure, at that composition C is the same composition where the boiling point is minimum. That is the azeotropic composition C. The trick, the graphs are like two convex lenses slanting downwards, but in negative deviation they will be protruding upwards. Why? Because their boiling point curve is lying above the ideal line. Because the vapor pressure is low, the boiling point will be more. Right? The upper graph, these graphs give the composition of the vapor, as you already know, over the liquid mixture at a particular liquid composition. The lower curves, these lower curves are the boiling points of the mixture at different compositions. But the liquid and vapor curves, the liquid curve is continuous, but the vapor curves are discontinuous. As a result, they meet at a single point C, where the liquid composition is same as the vapor composition. The intermolecular forces are so different, in this case so low, that at that point Raoult and Dalton, they have become friend. No difference between when you calculate using Raoult's law and then Dalton's law to find the composition of the vapor. You will surprisingly find that the composition of the liquid phase below is exactly equal to that in the vapor phase. But in other compositions, they are different. To the left of it, it will be richer and richer in the more volatile component. To the right of this, it will be richer and richer in the less volatile component. That's the beauty of the azeotrope. Now, supposing I tell you, I will give you a mixture. Let me tell you a concrete example where B is ethanol. B is ethanol, has a higher vapor pressure. Had they taken vapor pressure, it would have been greater. But this is boiling point. So boiling point of pure ethanol is lower, 78.2. I'm sorry, 78.4. And water, supposing, is 100. So this is less volatile component water. This is less volatile, more volatile component ethanol. Let's take for an example. And this composition is 98. It's not looking like 98. It should be, the C point will be very close to the 100% B. But for understanding purpose, let us presume that this is 95.6% ethanol and remaining 4.4% water. This is C. Supposing I give you a task, right? I give you a task, I give you 20% ethanol and 80% water here in this composition. This is the boiling point of that composition. Then you collect some liquid, its vapor will be having this composition. Raoult's law, then Dalton's law, this will be the composition of the vapor of this liquid mixture. And when you condense the first condensate, then it will have the same composition but has a lower boiling point. Again, when you carry on with the fractional distillation in fractionating column, you need not have to do in a successive manner. The theory that we understood, but in fractional distillation, we achieve all these thousands of distillation steps in one single column. So now this liquid, which is now having greater proportion of the more volatile component, because as you go to the right, supposing it was 20% ethanol, now maybe 40% ethanol, 60% water. So this. And again, if you boil at this boiling point and collect some liquid, so its composition will be here. Still say 80% of ethanol and 20% of water. And when you cool it, it will be the second distillate here. Then its boiling point will be lower. So when you keep it at its boiling point and collect some vapor, it will be having still more concentration of or proportion of ethanol. Finally, you come to this point. This point, when you come, the final distillate in the right side, that in the fractional distillation, when you collect, when the temperature goes on, decreasing and decreasing, and then finally constant, it will be exactly a constant boiling mixture, and you find there is no change in the composition of the vapor as well as liquid. So single point means the liquid composition below and the vapor composition above, they are identical. But in all other compositions, they are different. For example, here, the liquid composition is here and its corresponding vapor composition is here. And if it is here, the vapor composition is here. If it is here, vapor composition is here. And so, and if it is here, the vapor composition is there. If the liquid composition is here, the vapor composition is there only. So once you get an azeotrope, you cannot separate further. You cannot enrich the more volatile component B, say ethanol, further. So supposing in a very lighter vein I am saying, supposing I will tell you, dear one, I need a 99% alcohol and 1% water mixture for my medical purpose. I cannot take 20% alcohol. It's too dilute. I will give you a fractionating column, a distillation setup. Can you give me a 99% alcohol, 1% water? The answer is no. You continue to distill until the distillate will be a azeotrope. On the other hand, when the distillate is going towards the right, the residue will be moving towards the left. So residue will be richer and richer in the more volatile, less volatile component, and you will get pure water. So you will tell me in a lighter vein, sir, if you need pure water to drink, I can give you. But no, from 20% alcohol, I cannot make it 99. At the most, I can enrich to 95.6% alcohol. Be content with that. Ask your doctor to reduce your prescription level. I cannot do that. Of course, there are other techniques how to recover 100% alcohol from that azeotrope. That's not, distillation is not possible. Distillation is not the way. You might be knowing azeotropic distillation is something different, where you have to add another entrainer to just pull one of the components of the azeotrope out as a heterogeneous azeotrope. I am not going to discuss about heterogeneous azeotrope. We are discussing all about homogeneous azeotrope. It is a completely mixable liquid. The azeotrope is also mixable. Forget it, right? Similarly, when you now think, when you select, supposing I will give you a mixture which is 99% alcohol here and 1% water, right? I will ask you, you distill. I'll give you the fractionating column and I'll ask you to give me a 60% alcohol. I am too old. I'm an old man. I need 60% alcohol. You distill. Can you give me a 60% alcohol from 99% alcohol? The answer is no. Because as you continue to distill, the distillate will be richer. In these compositions, opposite thing will happen. The distillate will be richer and richer in the less volatile component, that is water. And the moment it comes to this azeotropic point, now see, this is the composition. And when you further distill, it will be still richer in water. And it will cool, it will be giving this point without change in composition. And in this manner, you will find, you will be enriching the composition of the percentage of water, the less volatile component, at the expense of decrease in the composition of the more volatile component. So when you reach 95.6% of alcohol from 99, you will come and tell me, sir, I cannot give you 60% alcohol by distillation method. Be happy with 95.6% alcohol. I cannot. By this method, no. Then I'll say, no, 60% alcohol, doctor prescription, I cannot. So, maybe you can drink it, just, I'm kidding. So, and conversely, what will happen to the fate of the residue? When the distillate is moving towards the left, towards the azeotropic point, then the residue will move in the opposite direction. It will be richer and richer in more volatile component. So in the residue, you will find 100% ethanol. So you can ask me and come, sir, do you need 100% alcohol, pure ethanol? I can give that. That is present in the residue, I can give that. But 60% alcohol from 99% alcohol, no chance. Right? So if you select any composition to the right of the azeotropic point, that is more than, say, for example, ethanol, water, example, more than 95.6%, then the distillate will give you the azeotrope and the residue will give you pure B or pure more volatile component, say ethanol. Similarly, if you choose any composition to the left of C that is less than 95.6% of ethanol, then on fractional distillation, the distillate will give you the same azeotrope and conversely, the residue will give you pure water or pure less volatile component. So in this positive deviation case, remember that the distillate will give you azeotrope and residues will give you either in one case pure A, less volatile component, or pure B, more volatile component, depending on from which composition you start your distillation process. If you start with a lesser percentage of the more volatile component than the azeotropic composition, you will end up with less volatile component in the residue as pure component. If you take a composition which has greater percentage of azeotrope of the more volatile component, then you will end up with pure more volatile components, ethanol, in the residue. And in every case, you will be getting an azeotrope in the distillate. Right? So I have written the same thing here. In case of positive deviation, the azeotrope is called a positive azeotrope or a minimum boiling mixture. Because at that particular composition, the vapor pressure is maximum, the boiling point of the mixture is minimum. It's called minimum boiling mixture. This is also a constant boiling mixture because the liquid phase and vapor phase have the same composition. Raoult and I funnily say Raoult and Dalton, they have shaked their hands at that particular composition. So no different. It is called a pressure maximum azeotrope. At that particular composition, vapor pressure is maximum. As the vapor pressure is maximum at this composition. At this composition. Am I going fast? Am I going fast? Will I slow down? Okay. That azeotropic mixture boils like a pure liquid without change in the composition of the distillate or the residue. If you handle an azeotrope and try to boil it and just reject some of the vapors and just put on a thermometer on the residue, I mean the liquid phase, you will find the temperature will remain the same. For example, 96.5% ethanol and 4.4%, 4.5%. I'm sorry, I wrongly wrote as 4.4. Yes, 95.6% ethanol and 4.4% water. You have that mixture and put a thermometer on that liquid and try to boil. Reject some vapor. Or you condense. You will find the temperature everywhere will be same. The remaining liquid, the condensate, everywhere the temperature will be 78.2. Once you land after distillation, once you land at the azeotrope, then no change will happen in the boiling point. It's a constant boiling mixture. It boils like a pure liquid without change in the composition of the distillate. So fractional distillation method cannot separate the components of an azeotrope. At azeotropic point C, the liquid and vapor curves, they meet. The two convex lenses, they meet at a single point, I have told you. That's the beauty. Same thing I have shown taking ethanol and water. Ethanol is 100% ethanol, 100% water, and this is the real graph. It is very acceptable graph. It is not acceptable. 95.6. Is it acceptable? 95.6 according to the scale. 95.6% ethanol is this point, and the pure ethanol has a boiling point of 78.5. I don't believe this. That's the reason why I was saying this author, from whom I have copy pasted, he says it is 98.5, but I say 78.5. I say 78.4. So whatever is the case, there is a 0.2 degrees Celsius decrease in the minimum boiling. This is the minimum boiling liquid at this particular point. So when you take any composition to the left, you go in this manner, the distillate goes in this manner, finally reach at C. At C, nothing will happen. And conversely, the residue will be giving pure ethanol. Water. This is the water. A is water. Pure water. Similarly, if azeotrope you will get in the distillate and pure water, less volatile component in the residue. Similarly, if you take a composition to the right of C, 99% alcohol, then again the distillate will give you C, the same distillate, and conversely the residue will be giving you pure ethanol. Let us concentrate on, I have already told you this, so no point in wasting time. Successive distillation or fractional distillation to the left of C, that is azeotrope. So liquid mixture having less than the azeotropic composition, 95.6 alcohol, produces azeotrope in the distillate, that is at the tops, and pure less volatile components, say water, in the residue, bottoms. Successive distillation or fractional distillation of any composition to the right of C, that is the percentage of alcohol more than 95.6%, produces once again azeotrope in the distillate and pure more volatile components, ethanol, in the residue. Just the opposite thing will happen in negative deviation. I will spend a very little time now and then wind up this lecture. Boiling point composition curves for negative deviation. Since vapor pressure at all compositions are lower than their ideal values, the boiling points of the mixture are greater than their ideal values. For a range of composition, the boiling point, just like for a range of composition, the vapor pressure were lower than the vapor pressure of the less volatile liquid. In the same manner, for a range of composition, the boiling points will be greater than the higher boiling liquid, that is less volatile liquid. For a range of composition, the boiling point is greater than more boiling or less volatile component. The maximum boiling point occurs at the azeotropic composition where the vapor pressure was minimum. At that composition, the boiling point is maximum. And therefore, you must be guessing that such an azeotrope is called a negative azeotrope or a maximum boiling mixture. That was a minimum boiling mixture for positive deviation, and for negative deviation it is called a maximum boiling mixture, and also it is a constant boiling mixture. The constant boiling mixture is applicable to both, but there it was a minimum boiling mixture, here it is maximum boiling mixture, and that was a pressure maximum azeotrope, here pressure minimum azeotrope. The acid, nitric acid water. This is a classic example where the azeotropic composition is 68% nitric acid and the rest 32% water. Having boiling point 120.5 degree against the higher boiling is water. 100 degrees centigrade is that of water, and pure nitric acid boils at 86. It is more volatile, and water is less volatile, having higher boiling point. The azeotrope at this composition, 68%, is the highest, 120.5. So not that this is the only percentage where the boiling point of the mixture will be greater than 100. There are a range of compositions where the boiling point will appear more than 100. But this is the composition where the boiling point is maximum. Now same, this is called a negative azeotrope or pressure minimum azeotrope or a maximum boiling mixture. It is also called a constant boiling mixture as the composition of the liquid phase and vapor phase. Same, the manner in which we discussed the positive deviation, this is the same. Hence, its composition doesn't change on boiling, so it's not possible to separate the components by distillation. So, azeotrope cannot be separated by distillation method because the distillate and the residue will have same composition. Now, this is the graph. These two convex lens, they are pointing upwards. You know, this graph, the blue graph, is the boiling point graph of different compositions. This is the boiling point of, say, A, which is less volatile, less volatile, and this boiling point of B, which is more volatile, say nitric acid, 86. This is 100, this is 80. This is the boiling point curve, and this is the boiling point of the mixture at different compositions. Now this superimposed, what's that, red? Pink color graphs, these are the vapor composition graphs. This is the vapor composition graph to the right side, this is the vapor composition to the left side, and this is a single point where the two curves meet. The single point, that is the azeotropic point, where the vapor phase and liquid phase, they have same composition. But in all other cases, they are different compositions. In all other compositions, vapor and liquid, they have different compositions. But, at this particular composition, liquid and vapor have same composition. As I funnily say, Raoult and Dalton, they have become friend. They have shaken their hands at that particular point. Right? Now tell me, if you select any composition to the left, supposing this is nitric acid 68%, this is 68% nitric acid, and remaining 32% water. Supposing I give you at this point, say 40% nitric acid and 60% water, because it is closer to 100% water. So it is 40% nitric acid I give you, and I give you the distillation flask, fractional distillation flask. What you get? If this is the composition of liquid, the corresponding vapor composition is here. Raoult followed by Dalton, the composition is here in the reverse direction. And it's, if you let me hold a pen to show you. Let me not be very fast. I know I am not interested in getting quick response and quick popularity by producing a short video of 20 minutes, 10 minutes, so that I will get hundreds of likes and subscribers. Because my tech from the video production is to go to the deep root, to go to the concept, and therefore I cannot compromise with time. Popularity is nothing to take away my commitment to the conceptual aspects. Maybe in future years, if YouTube continues to retain my things, then it can get more and more likes. Now, let me tell you, supposing I give you this, say 40%, 40% nitric acid and 60% water. Then in the distillate, the vapor will be richer in the less volatile component. And when you cool, then it will be giving the first condensate, having a lower boiling point. And it has got its own vapor, which will be again richer in the less volatile component. In this way, the distillate will be giving you pure water. On the contrary, the residue will move towards in the opposite direction, and residue will be richer and richer in nitric acid till it reaches the azeotropic point C. When this composition comes, where Dalton and Raoult have shaken their hands, the vapor pressure, the composition of the liquid and vapor, they are same. At that point, nothing will happen. You cannot enrich nitric acid percent by further distillation. However, how much distillation you may make, the percentage will remain the same at C. So at the most you can give me from 40% nitric acid to 68% nitric acid, of course by mass, this is W by W, but not above that. In the residue, in the distillate, you give me pure water, pure less volatile component. Similarly, if I select a composition to the right of 68%, right of the azeotropic point, I give you supposing say 80% nitric acid and 20% water. So at this point, so as you distill, the distillate will be richer and richer in nitric acid, which is more volatile because it is heading towards right, and ultimately in the distillate you will be giving me pure nitric acid. 100% nitric acid you can give me in the distillate. On the contrary, if you go and find what has happened to the residue will be reaching point C. The moment the enrichment of the less volatile component comes to 32%, that means 68% nitric acid, no further enrichment of the less volatile component. That 68-32 will remain fixed forever. As long as you do not adopt some other technique, not distillation technique, other technique to separate them, right? So in this case, just the opposite. Successive distillation or fractional distillation of at any composition to the left of C, the azeotrope. Say less than 68% HNO3, I gave you 40%, produces pure less volatile component, say water, in the distillate tops, and the azeotrope in the residue bottoms. Because the distillate is heading towards left. This means it's distillate. Their distillate was heading towards, in the opposite direction. And the residue will be reaching C. As the moment it reaches C, nothing can happen. Similarly, if I give you successive distillations or fractional distillation at any composition to the right of C, greater than 68% nitric acid, say, produces more volatile component, that is nitric acid, in the distillate, and same azeotropic mixture in the residue at the bottoms. This is opposite to what we observe for positive deviation. So at the end, we have concluded. I will tell you the conclusion. Let me see how many minutes have gone. It is 1 hour gone. So you will conclude of yourself by viewing once again some examples of mixtures of having positive deviation. The classic example I used to say is ethanol water. It's, no, let me make it 4. The A is the more volatile, B is less volatile. Its boiling point is, I should correct it because I have corrected there. I believe it is 78.4 degree Celsius, and pure water is 100, but the azeotrope is 78.2 degrees Celsius. And the composition with the A, that is the more volatile component percentage is given, A, W by W, 95.6%, and the rest water is the azeotropic composition of ethanol water mixture, showing positive deviation. Similarly, carbon disulfide acetone, that also is positive deviation. Carbon disulfide has the boiling point pure 46.3 and acetone 56.5, but the azeotrope is lower than, much lower than the lower boiling liquid, that is more volatile liquid. It is way below. It's not like ethanol water, only 0.2 below. It is way below the lower boiling liquid. And the composition is 67% of carbon disulfide, A, by weight. Now let's see some negative deviation liquid pair. All acid and water, and some organic acid, organic base like phenol, aniline. Right. So nitric acid, water. Nitric acid is more volatile, 86 degrees Celsius is the pure nitric acid, 100 is water, and the azeotropic composition is 68% A. A means this one, more volatile component, that is 68% nitric acid. And its boiling point is even much greater than the higher boiling liquid, the less volatile liquid, 120.5. Now here I have put it in a box. It is because sulfuric acid I have taken as A. Because I will give you the percentage of sulfuric acid in the azeotrope, that is why I kept it as A, but sulfuric acid is less volatile. Its boiling point is 290. I think I wrongly somewhere told 270. I'm sorry, 290. And water is 100. In all other cases, the first one is more volatile with lower boiling point, and the second one is less volatile with higher boiling points. But in this case, it is the opposite. Therefore, I have demarcated so with a distinction mark, where sulfuric acid is deliberately kept in the left so that percentage will be of sulfuric acid 98%, 2% water. So, and now see the remarkable increase. 338 degrees Celsius is the boiling point of 98% alcohol. 98% sulfuric acid by weight. If it is 100%, it is so less, 290. Because at that composition, the vapor pressure is so low that the boiling point is much greater, highest. In all other composition, it will be less than, range of composition, it will be less than this, but more than 290. But less than 38. This is the highest boiling point. Chloroform acetone. Acetone is more volatile. Chloroform is less volatile. And it's 20% of acetone. It shows the highest boiling 64.7, which is greater than the higher boiling liquid. HCl water. HCl in the native state it is a gas, but we treat it as a fluid. As a liquid system in the mixture where its boiling point is -84 and water is 100. But see, 20.2% HCl solution has a boiling point of 110, while pure liquid HCl, supposing you liquefy HCl, we are talking about liquid HCl, is -84, and liquid water 100. But 22.2% of HCl will have a boiling point 110 degrees Celsius. That is a negative azeotrope, negative deviation. HF is, pure HF is -19.5 and water 100, but 35.6% HF is the azeotrope of HF water, and that boils at 111.35, right? So at the end, let me tell you, ideal mixtures which we studied in the previous video do not have any azeotropes, like benzene, toluene, like hexane, heptane, like methanol, ethanol. These do not have any azeotrope. They have one convex lens in the distillation graph, in the boiling point graph. One vapor and one liquid, so they form only one from one y-axis to other y-axis. So cleanly you can separate the more volatile component in the distillate and let me see you, and the less volatile component in the residue, more volatile component in the distillate. The components are separated completely in their pure states by fractional distillation. How did you like the program? It's to me, it's a very conceptual topic, and if you have really enjoyed, please give a thumbs up, and not only thumbs up, but also subscribe. Many of you have not subscribed, not because you didn't want to, but because who does it? It's a time-consuming process. Just to put a button on subscription will make you more attached with this instructor, and all the videos will be, the links will be immediately getting. The sooner I upload, you get the link, the fast you get. So subscribe whenever you like it and you want it. Bye bye.